All right, great. So this talk will be a little bit new to this community and kind of basic and high level, but I hope you enjoy it. We'll see. Okay, so this is a paper about information. Let me just start by telling you what I mean by information in this talk. So I'm thinking of a bunch of random variables that are drawn from a joint distribution together. And we really just care about x. We want to learn about x. And I'm thinking of these y's as signals that will just give me information about x. Okay, so that's the model. What else is this paper about? It's a paper about substitutes and complements. By substitutes, intuitively, I just mean diminishing marginal values. So the more I have of everything else, the less valuable this thing becomes to me. And we're used to hearing about substitutes and complements in the context of items or goods. And I would argue that they've been almost unreasonably effective, both in economics, where they capture the existence of market equilibria, existence of stable matchings, and in algorithms, where, especially if you model substitutes with submodularity, they correspond, they characterize efficient algorithms for a lot of classes of problems. So we're trying to answer a very broad but tempting question, which is, could you have some sort of similar ideas happen with substitutes of information, and what would that mean? So intuitively, I think it makes sense. The more I know of other things, the less useful this information becomes to me. But I do want to highlight a couple challenges or example roadblocks that would come up. Right, so for items, you're just given a valuation function. That tells you what the value of the items are. But what should the value of information be? Are you curious to learn it? Are you using this information for a purpose? And how does that inform its value? Okay. For items also, the value of one item doesn't have to depend on the value of another. They can be related in any way. It's just personal preference. But pieces of information can be correlated. Their probabilistic structure seems like it should constrain their relative values, and it's not clear, how that comes in. So in trying to answer this question, before we can even define substitutes and complements, this became for me really about a story. Okay, and the story is, what is the value of information? How do you measure the usefulness of information or amount of information? Okay, and any story like this has to start with Shannon, who said, use this function, right? He said, you can take the entropy of x, and then you can take the conditional entropy of x given y, and this will tell you how much information y gave you about x, right? Which sounds good, but in 1966, Ron Howard said, information's value should depend on the use you're putting it to and the choices you're making as a function of that information. And so he proposed this very general model, which is what we use in this paper to define value of information. Okay, so we have a decision maker who knows the prior on x, and they have to choose from some set of decisions. So for example, bring their umbrella to the conference today or not. Right? And then simultaneously, nature is going to draw this random variable x from a distribution. Here, x could be either rain or sun or clouds. And I want to mention this might seem like a frivolous or silly example, but you should think of this decision maker as the Wicked Witch of the West. And so, this is actually a very vital problem. We're playing for keeps in this paper. Okay, and they're going to get some utility that's a function of the decision they took and the outcome that occurs. Right? And then we can write, value v of the empty set for the expected utility if they're deciding optimally, where empty set means no signals. They didn't get any information before making this decision. Okay, and I'm always going to assume that they decide optimally, so they're able to solve that problem. Don't worry about how. Okay, and then Howard said, all right, now what if Elphaba here gets to observe this random variable y first, update to a posterior, and then decide whether to bring her umbrella or not. Okay, and then she'll get a better utility on average because she'll make better decisions. Okay, and we can call her expected utility in this scenario v of y because she got to observe y. And you could extend this if she got to observe a set of signals, v of that set. Okay, so this is really nice, and this is our model for value of information. But it doesn't say how tractable this is or how you should deal with this mathematically or even intuitively. And that's where the next part of the story will come in. Okay, sorry, I should say, so the marginal value of y, right, will be this difference, v of y minus v of the empty set. That was the marginal value of y. Okay, so in '71, Savage kind of wrote the book on what are called proper scoring rules. And you can think of them, although he didn't, in the same framework as Howard. So proper scoring rule is a special case where the decision is to commit to some prediction about x. So commit to saying this is the distribution over x that I think will happen. And the score, the utility is some scoring rule, some s, which is a function of that prediction and what actually happened. Okay, in such a scoring rule, this s function is called a proper scoring rule if the optimal decision to make here is just to say your true belief. Whatever you believe the distribution of x is, you should say it. And the intent of these is to elicit predictions from experts. So the idea was ask the expert to commit to a prediction, observe some outcome, pay them with the scoring rule. They want to be truthful. And let's just see an example. So this beautiful log scoring rule. You get paid the logarithm of the probability you assigned to the thing that actually happens. So if someone offers you to pay you with this rule, you should be truthful. You can take my word for it or prove it for yourself later. And the key point about these is they're very tractable because they correspond in a really cool way to convex functions. Here's what I mean by that. For any proper scoring rule, I can trace out your expected score as a function of what you believe at the time you predicted. And it'll always be convex. So here I have a binary x. This is your belief, and this is your expected score. So for example, if you just believed this prior, you would predict it, and you'd get a pretty low expected score. But if you get a signal y first, you'll update to some posterior. So one outcome you'd update to this, another outcome to this, and you get a higher expected score on average if you're predicting given that information y. This black bar is measuring Howard's value of information, or marginal value of y. Okay, and this figure might look familiar from a few slides ago. This is actually Shannon's figure flipped. The reason is that for the log scoring rule, this function is exactly the negative of the entropy function. Okay. For other proper scoring rules, that's not going to be true. It'll be some other convex function. And you can think of these as kind of generalizing Shannon's way of measuring information to specify to the decision problem or the proper scoring rule that we care about. Okay, and I kind of hinted where I'm going next. So this is true for all decision problems, not just proper scoring rules. And this is an observation that goes back at least to Savage in 71, but we really had to kind of develop it and use it strongly in our paper. So, any weird utility function you have, any decision problem, I can plot this convex expected utility function, and I can reason about value of information just by reasoning about these sort of Jensen inequality gaps, this marginal value of information by plotting it in a convex function. Super cool. Okay, so that's value of information. What is this paper about? It's about defining substitutes and complements for information. And so let me give you the intuition from this plot. Imagine now I had a second signal z. Okay, so I'd update some posterior based on both z and y. One of maybe these four posteriors if they each had two outcomes. And on average, my expected utility in this decision problem, for example, with the scoring rule, is going to be even better. But this marginal improvement of the second signal was not as large as of the first. Right? That's the idea of substitutes that I want to capture, the intuition. Diminishing marginal value. So if I were to get a signal first, it'll give me quite a bit of marginal value. If I get it later, it's less. Okay, and formally, we can just capture this with submodularity. So if you haven't seen the definition of submodularity before, it says if I look at this yi and I look at its marginal value over some set of information I already have, that's going to diminish the more I know, if I know more. Okay? And we define complements with supermodularity where the inequality is flipped, and that's increasing marginal value. So an example of complements is the XOR of two random bits. Right? The first bit you get is not going to move your prior at all. Your utility is not going to change. The second bit is going to tell you everything you need to know. Your value will be very high. So increasing marginal value. Okay. So that seems nice, but actually it will break down because information is divisible. Right? So I can take in a signal that I have and choose to reveal just some piece of it. The colors aren't showing up well here, but this person has taken just a piece of their signal and passed it on. Okay, and as Benjamin Franklin said, telling half the truth is often a great lie. Okay, so the definition I gave you in the previous slide is going to completely break down in some cases because agents will be able to just garble their signal or only reveal a piece of it. And today I don't have time to tell you our solution to this in detail, but the idea is to just extend the definitions to deal with marginal information that captures these sort of fine-grained garbling. You need to have diminishing marginal returns for even noisy pieces of a signal. Okay, and that's all I have time to say about it today. And I'll tell you what this TCS plus talk is at the end. Okay, so that's what I wanted to say about the definitions. What else is this paper about? You have to have applications if you're in computer science, I guess. So really the main result is an equilibrium result for prediction markets, which I'll tell you about next. And then we also have some evidence that these definitions could be important in algorithms for the complexity of acquiring information and choosing which information to acquire. And I'll tell you briefly about that. Okay, so what's a prediction market? The idea is that there's a bunch of agents out there with these pieces of information, yi, and we want to just aggregate them into a good prediction about x. Okay. And so we're going to design some mechanism where they can come one at a time and make their predictions, and they'll be Bayesian and rational, so they'll be updating based on what previous agents say, and this information will all get aggregated, and everything will be great, depending on the equilibrium properties. Okay, so here's what the mechanism looks like. And I want to mention that you can actually view what I'm about to say in terms of buying and selling shares like you're in a stock market. There's this really cool duality, but I'm going to tell you the proper scoring rule version. So if you just had one participant, the market structure would be a proper scoring rule. They would tell you their prediction. You'd wait, you'd observe the event, you'd pay them with a proper scoring rule, and we know that's truthful because that's the definition of a scoring rule. So for example, the log scoring rule. Okay, when you have two participants, what you're going to do is pay the second one by the marginal improvement in score that their prediction makes. Okay? So you're going to take the score of theirs minus the score of the previous one, and this is still truthful for both participants. First agent wants to be truthful, they face a proper scoring rule. The second agent faces a proper scoring rule minus a constant they can't control. So it's still truthful for them. Okay? And because they're Bayesian, they'll aggregate the previous information, they'll update based on it, and you'll get a good aggregation. Okay, so if you understand proper scoring rules, which we have done for 45 plus years now, this is completely trivial. So let me change it once more. I'm not going to add a third participant. I'm just going to let the first participant come back again. Okay? And again, they'll get paid with this marginal improvement. And now our understanding of what happens here in equilibrium drops off a cliff. So we really don't have good understandings of what happens in this simple game. Okay, let alone a full prediction market where everyone is getting paid by marginal improvement. The reason is that this purple person, let's call her Alice, she could do almost anything at time one. She could tell the truth about what she believes. She could just withhold everything she knows. She could say something crazy and try to deceive Bob into making a really bad prediction so that she can come in later and scoop up a whole bunch of money by correcting that prediction. And that's a danger that we don't have good tools for addressing. And so here's all the research, all that we knew about this problem. So for the log scoring rule in particular, it's the only one that's been studied with results. For one particular information structure, this conditionally independent, Alice actually does want to be truthful on day one. And that's really good because then when Bob is truthful on day two as well, information gets aggregated quickly. And they were able to boost this. You can boost this result to show in a general prediction market. Agents will rush to be truthful. So no matter how many of them there are and how many times they get to trade, all the information is aggregated as soon as possible. So it's sort of the perfect world. Okay, and then this next paper showed that if these signals are independent, so a different information structure, and the log scoring rule, you get the opposite effect. Alice delays saying anything until the third day, and then you boost this for a general prediction market. Everyone is delaying and information is not aggregated until very late. Okay, so the contribution of this paper here is to sort of characterize when these two opposite cases occur. Okay, and it may not be too surprising, but if and only if signals satisfy substitutes according to the stronger definition I mentioned, which takes into account sort of pieces of signals, then the only equilibria are these good all-rush things where everyone is truthful as soon as they have a chance and information is aggregated as quickly as possible. So you may have heard of this efficient market hypothesis, which says that information is incorporated into prices immediately in economics. And you could view this as a sort of the first formalization I know of when this happens in general, but in these like very simple stylized markets, these prediction markets. Okay, and then for complements, you get the exact opposite behavior. So everyone waits and waits and waits, and you get this sort of failure because information is not going to be aggregated until the very end. And the proof of these isn't completely trivial. but it's close, and the intuition is completely trivial. So substitutes means diminishing marginal value, right? So we're using this proper scoring rule, where it's basically rewarding you on average by the marginal value of your information. So you just have to kind of formalize that fact with this marginal improvement. And then diminishing marginal value means the longer I wait, the less I'm going to get a profit if I'm a trader in these markets. Okay, so that's all I wanted to say about prediction markets. So let me talk about algorithms. Okay, so we define this sort of general algorithmic question, which is inspired by, there are similar questions studied, but I'll mention that later. You're given this utility function I talked about in this decision problem, and you're given the distribution. And you have to be given these as oracles because they may be exponential sized. And let's say you're also given an oracle for optimizing your utility function. So I'm not worrying about the complexity of that problem. Okay, and then you're also given a price tag, let's say, for each of these signals. And you have a budget constraint B, so you want to decide, for example, these are a whole bunch of data sets, Y1 through Yn. Which ones should I purchase in order to solve my problem? Okay, and I know the distribution sort of what's in these data sets. A special case could be a cardinality constraint. So, for example, you have K sensors, and you can put those K sensors anywhere in the environment, and there are N possible locations. And where should you put those sensors to optimize your objective? Okay, and so basically we just show kind of a simple, obvious thing that, well, in hindsight seems obvious that it's tightly connected to set function maximization. And in particular, if you have substitutes, if these signals I told you were substitutes in the beginning, then I can reduce this to submodular maximization of set functions, which hopefully people are familiar with. That's something we can solve to a good approximation in polynomial time. Okay, and the fact that the items were substitutes, or that the signals were substitutes, means that this problem is submodular. But then you can also get a reduction in the other direction. So given a set function you want to maximize, I can construct a problem that looks like this, so a distribution and utility function, so that if you were able to solve that, you could maximize the set function. Okay, and that means that hardness results transfer over. And in particular, if you have complements or you don't have any promise about substitutability, you can't guarantee an approximation factor quickly. So I just want to emphasize the idea of this problem is definitely not new. Like information acquisition type problems have been studied. And even the idea of using submodularity to solve them is not new with us. But the literature seems to be focusing on other questions. So they're focusing a lot on in what sort of information models can I efficiently query this oracle, whereas we abstract that out. But anyway, if you're worried about that, you can think of the contribution here as more of just showing that the idea of substitutes, of informational substitutes, seems kind of fundamental to the complexity of this problem. Like if you care about the complexity, then you have to sort of worry about substitutes. Cool. Okay, so I think that this is kind of a paper about shadows and the shapes that they make that ignores the objects casting the shadows, by which I mean substitutes and complements themselves. So I haven't really given you concrete examples, except for some mentions of prior work that can be shown to fall in that category. And we don't know a whole lot of good examples of sort of classes of decision problems, or these convex functions, and classes of distributions of information structures and how they interact to actually form substitutes and complements. So that's a big challenge that we need to solve going forward, is just understanding these better. And we do have a few examples, and I think we get good intuition from these plots I showed you. Just all you have to do is look at convex functions and look at where the distributions put posterior beliefs on the horizontal axis. So we're getting there. But and then I would also say that this is more a paper about possibilities than about what we've achieved so far. I think that we've shown some promise that this could be interesting and could have good applications, but I don't want to leave you with the impression that I'm satisfied with our understanding here. So, we really, only time will tell, time and more research, whether this can really put down roots and start growing. Okay, so maybe I can quickly mention, so in game theory, you can think of a whole lot of areas and ask, could this apply? And the answer seems to be that it can be difficult, because as soon as you go to multiple agents, with multiple preferences, you need things to be substitutes for all of them maybe, and we haven't started thinking about that yet. There's a lot of algorithmic questions, and just like I said, questions of what are the structures of substitutes and complements. Okay, and I want to mention quickly that so there's this cool series of online video lectures called TCS Plus that a group of students organizes, and they kindly invited me to talk about this in a month, so you can hear more about this topic then. And so I'll stop and take questions. Thank you. Yeah, so the question was, do I know it's tight with like 1 minus 1 over e for substitutes? I think it should be because, you know, you have examples with set functions where to do better than 1 minus 1 over e with a submodular is NP hard or something, and I think that should still transfer. Ooh, okay, is there a relation to privacy? I am embarrassed to admit this to you, Salil, but I haven't thought about that, about privacy in this context yet. It does seem, yeah, it seems actually very related intuitively. So you can also think of like sensitivity of a function, like in Boolean function sensitivity. You know, if one thing controls the output a lot, it seems very complementary. So I think your intuition's on, but I don't know.